Good afternoon, all of you, and welcome to the 12th lecture of STAR 2026. In this lecture, we will be hearing on visible light astronomy by Professor Anandamayi Tej from Indian Institute of Space Science and Technology, Tirunelveli. Mr. Hafiz Nasir will be moderating this session. I would like to introduce Mr. Hafiz. Mr. Hafiz is currently in the 4th year of his PhD research. His research is primarily focused towards understanding the formation of massive stars. He uses multi-wavelength observations in radio, submillimeter, and infrared for his investigations. Over to Mr. Hafiz.
Hi, thank you, sir, for the kind introduction. So a very warm good afternoon to all. So I'm here to moderate the session and introduce our speaker, Professor Anandamayi Tej. She's a faculty member in the Department of Earth and Space Sciences at the Indian Institute of Space Science and Technology, Tirunelveli. She currently serves as a Dean of Academics now. So she has been associated with the institute since its inception. So Professor Tej obtained a PhD from Physical Research Laboratory, and later she carried out a postdoctoral research at Observatoire de Strasbourg and Tata Institute of Fundamental Research. She has also been a visiting scientist at the Space Telescope Science Institute. So her research majorly focus on high mass stars, particularly their formation process and the feedback mechanism in the interstellar medium. And today she is here to give a lecture on the effect of atmosphere on the incoming radiation and the need for space-based observation. So I'd like to invite Dr. Tej for the lecture. Over to you, ma'am.
Thank you, Hafiz, for the introduction, and good afternoon to all the students who are participating in this program and are currently there to listen to this talk. So very good afternoon to all. So I will share my screen, and Hafiz, you can tell me whether everything is fine or not, okay?
Okay, ma'am, sure.
Yeah. Can you see my screen? Yes, Hafiz?
Yes, ma'am.
So the laser pointer is also there?
Yes, ma'am. That is
okay. Yes. So in this talk today, I will be actually presenting to you how the atmosphere influences our observations. And particularly, I will discuss about the visible light astronomy in this perspective. So it is not what I am going to discuss is not restricted to visible light. It is also true for other part of the electromagnetic spectrum. But I will give you some examples from visible light astronomy. So as all of you know that astronomy and astrophysics is basically how we explore or how we try to understand the universe. It is like exploring the vast universe, be it solar system objects like Jupiter, how the bands are formed, or like the rings of Saturn, Neptune, etc. Or this is the pillar of creation, how stars are formed, how galaxies are formed, how stars evolve, how galaxies evolve. So it is a wide spectrum of physical processes and objects that one probes in astronomy and astrophysics. And how do we do that? We do that from understanding the radiation that we observe from these sources. So these objects, they radiate over the entire electromagnetic spectrum. And what we try to do is we try to understand what is the time variability of this radiation coming, what is the energy distribution of this radiation coming, because all this will depend upon the nature of the sources. It will depend upon the physical processes that are going on in these celestial objects. So these photons which are coming from the far-off celestial objects actually carry the information about the physics of those objects. And the astronomers, they observe these photons or they investigate this electromagnetic radiation coming, and from there they try to build a story about the nature of this object, and that will help us explore the universe. So this is a picture of the full electromagnetic spectrum, right from gamma rays to radio waves. So as you know, the wavelength increases in this direction, the frequency increases in the opposite direction. So we have the entire electromagnetic spectrum to study. Now the energy distribution of this electromagnetic of the energy distribution as a function of the frequency or wavelength will solely depend upon the nature of the source, as I just mentioned. For example, if I'm looking at stellar objects, I can say that they will follow the black body radiation, and where the black body peaks will depend upon, say, the surface temperature of the star. From that, we can know what kind of star that is. So when I look at this entire electromagnetic spectrum, as you can see, we have, like, we can study in gamma rays, we can study in X-rays, in ultraviolet, in visible, in infrared, and in radio. And what I'm going to focus today is this very, very narrow stretch, which is the visible light. Now, okay, I have the celestial objects which are radiating, and I want to observe them. And if I'm at ground or I'm using the ground-based telescopes, let us see what happens, because when we observe from ground-based telescopes, we have the atmosphere above us. Does this atmosphere play any role, or the atmosphere is redundant? It is just above us. As we know also from our general knowledge that the ozone layer in the atmosphere helps us here because it does not let the UV radiation to penetrate down, which is harmful for life here. But the atmosphere puts an obstacle for astronomers, because the atmosphere, this cartoon that I'm showing here, here are the windows, that is the electromagnetic spectrums that I showed earlier, and this is the altitude in the atmosphere, and this is the ground which is shown in green. So as you can see, that the atmosphere is transparent at only certain wavelengths. So the right-hand side cartoon also shows you the same thing that I have shown in picture here. So the atmosphere is completely opaque in this part of the electromagnetic spectrum. There are some windows in the optical and the infrared that the atmosphere is transparent. Then again, it is completely opaque. And in the radio part of the electromagnetic spectrum, the atmosphere is transparent. So these are the windows where we do observations. And luckily, it is transparent in the visible light, and our eyes are tuned to the visible light. If it would not have been transparent, we wouldn't be seeing the universe at all with our naked eyes. And this cartoon here, this plot here shows what are these absorbing molecules, which are the molecules which are responsible for making the atmosphere opaque at certain wavelengths that we see here. Mostly you would see that water vapor is the main culprit, which does not allow all the radiations coming from the celestial objects to reach us. So here also, if you carefully see, it also shows in which part of the electromagnetic spectrum, what kind of observation you can see. So these are all space-based observations here. This is ground-based in the optical and in the radio, and in some part of the infrared, you can have airborne observations also. Okay, so now let us say that we are observing a star. So when we observe a star through a telescope, let us say this is the diameter of the telescope, and I have a parallel beam of light coming from a star. The stars are far, far off. So the radiation coming from them will be a parallel plane wavefront, which is reaching our telescope aperture. So due to the diffraction at circular aperture, those who are physics students, they will know that due to the diffraction of circular aperture, what we actually obtain is the Airy's diffraction pattern in our focal plane. So this Airy's diffraction pattern, it has a central bright spot, then there are concentric dark and bright rings. So almost 84% of the light is there in the central bright spot here, and that is known as the Airy's disk, and that is what we see in stars. You see my background here. So these are stars, and what we are seeing is actually the Aries disk here, because these are too faint and it gets immersed in noise. And when I have two of these Aries disks, like I have two stars, I am looking at two stars in the sky, then if the Aries patterns are well separated, I will tell that they are well resolved. I can see the two stars and two separate ones. Now this is just resolved. When you have the maxima of the second falling on the first minima of the first. So that is when I say it is just resolved, and this is an unresolved case. So here comes the resolution criteria, and this was given by Rayleigh. This is the Rayleigh's resolution criteria. And just to tell you that this diffraction at circular aperture that follows a Bessel's function, and this is where it goes to 0. And from there we obtain the resolution criteria, which says that my delta theta is 1.22 lambda by d1, where d1 is the aperture of the telescope and lambda is the wavelength at which we observe. So the larger the telescope, the finer details that I can see. So my resolution is much, much better if I increase the aperture of the telescope. So when I increase the aperture of the telescope, I am not only gathering more and more photons, my light gathering power increases, but the resolution also improves. I can see finer and finer details. So going over, so okay, I have a resolution criteria. I have a certain diameter of the telescope. So the diameter of the telescope will tell me whether what separation I can actually discern, what separation between the celestial objects I can actually discern. So if that is the case, then what does the telescope do? Because we see the starlight through the atmosphere. Now here the parallel lines are like, I am visualizing the atmosphere to be in layers like this. The density increases in this direction. So the refractive index also increases in this direction. So if I have a star here and I have incoming light coming from the star, which is passing through my telescope, because of refraction, it will get bent and bent. So even if the star is here, I will see the apparent position of the star there. This is not a problem. Instead of seeing the star here, I will see it here. But the problem comes is that these layers are not static. They are continuously moving. In the atmosphere, over my telescope, I have air cells. These are small packets of air, that moves around, and they have different refractive index. So what it does is, so now if these layers are moving, what I am observing is that the star is dancing around. So if the star dances around, what happens to this resolution that I am talking about? How does this affect the resolution that I just discussed? So let us have this cartoon again. So I am looking at a star, and this is the turbulent atmosphere through which the starlight is passing and falling on my telescope, on my detector. So because of this turbulence, this yellow spot here, yellow circles are actually my Aries disk. So that, again, to repeat, it is dictated by the diameter of the telescope aperture. So I can, if I have very, very fast sampling of the star, then I can see the Aries disk. That means I'm going to the theoretical diffraction limit of the telescope. But because of this turbulent atmosphere, these Aries disks will be dancing around. So if I want to take a longer exposure, which is longer than the time scale in which the atmosphere is actually changing here, then if I take a longer exposure, I will get this big blob here. So which is much, much poorer resolution than what is my theoretical resolution dictated by the telescope size. Now coming to this again, so here if you see, this is my telescope aperture. Yeah, I have another notation, small d, but this is same as my capital D1 there. So this is the plane wavefront coming, and it makes an image here. So this is, say, for a Hubble Space Telescope, you have 2.4 meter, it would make an image of the size of 0.05 arcsecond. But then, as I said, atmosphere is not stable. I have such air cells of typical size of some 10 centimeters, which are moving around. So when they're moving around, they actually form an image in a longer exposure. When I say longer, longer than the time scales of turbulence, I get a 1 arcsecond image. So my turbulent atmosphere limits my angular resolution. Not only that, as I told you, these are of the order of 10 centimeters. So even if I have a large telescope, say 10 meter like the Keck telescope, or 30 meters like the planned 30-meter TMT telescope, my resolution will only be of this, what I would get for a 10 centimeter telescope. So unless and until I beat the atmosphere, I will be limited in my angular resolution. So for ground-based observation, my limit to the angular resolution comes from my turbulent atmosphere. Not only that, these air cells will be moving. So it will also give rise to fluctuation in the intensity of the starlight that I am observing, which is known as scintillation. The wandering or dancing of the star is known as seeing. This is a terminology used by astronomers. So seeing limits angular resolution, and the fluctuation in intensity, which is known as scintillation, limits my photometric precision, because my noise will be continuously there, and from that noise I have to filter out the important information about the target. So now this can be resolved because we are building larger and larger telescope on ground, because we need to collect more and more photons so that we can go to fainter and fainter objects. And when we go to fainter and fainter objects, we are going actually back in time. So we can beat the atmosphere by using something called the adaptive optics. So here this is a adaptive optics system. Briefly, if I tell you, it has a deformable mirror, which actually, with the help of mechanical actuators, can actually move this. It is made of small actuators are here, and when a deformed wavefront falls on them, the actuators actually move and the outgoing wavefront becomes a plane wavefront. So in principle, we are beating the atmosphere by, so suppose this actuator will feel that this part of the wavefront needs to be pushed up, then it will push it up. So this part of the wavefront needs to be pushed down, it will push down this part of the mirror, so that I get a very clean and nice plane wavefront coming out. So and this is done by something known as the wavefront sensor. Mostly they use a Sharp-Hartman wavefront sensor, which is an array of lenslet. So in case it is a plane wavefront, I will get a very nicely arrayed images at the center of the lens where it should be. If I have a distorted wavefront, then it will be scattered all around. Then I can model it to see what is the distortion and give a real-time feedback to these actuators that your wavefront needs to be corrected in a particular way. So in principle, with this adaptive optics, we are correcting the turbulent, the distortion made by the turbulent atmosphere. So if I show you some example, so this is a blob that you got without adaptive optics, but when you do adaptive optics, this is actually two stars sitting here. Because of turbulence, it was just blurred into a big blob here. Now the movie I'm showing on the right-hand side shows you the galactic center. When adaptive optics is not there, you hardly see anything there. It's just a fuzzy thing. With adaptive optics on, you see that there is a bunch of stars here, and these stars, the kinematics of these stars were used to get the mass of the supermassive black hole at the center of our galaxy. But this is not foolproof. You cannot get 100% correction with this. And especially in the visible part of the electromagnetic spectrum, you can hardly correct it because the distortion of the wavefront is very, very large. You can maximum go to 70% of 80% of correction using adaptive optics, but you cannot go to the diffraction limit, the theoretical using adaptive optics, but you cannot. So that tells us that we need to go to space. So why we need to go to space? Because if from ground base, we will have turbulence, we will have variable in refractive index, we will have a large scale, small scale atmospheric turbulence, so which will result in blurred image, or the image that there is a terminology used called the point spread function. It is actually the image of a point source, which is affected by the diffraction, the diffraction at the circular aperture, and also the atmospheric seeing that we have, and also the intensity fluctuation. So from ground, it will be distorted, noisy, and unstable. Space, there is no atmosphere. So we will have an undisturbed wavefront. And what we will have is sharp, stable, and precise photometry and stable imaging. So just to sum it up, from space, we can have diffraction limited imaging, which will give us stable and sharp point spread functions. We can do deep imaging because we will have very low and stable background from Earth. When we are observing in our atmosphere, we have air glow, we have disturbances. So the background is also very high. From space, that is not there. So we can go in for long integration. We will have very stable photometry because we won't have those fluctuation in intensity, which I referred to as scintillation. And then there will be time stability. There won't be any weather constraint. And there won't be any time constraint, because in the visible part of the electromagnetic spectrum, when we observe from ground-based facilities, we are only restricted to after twilight and before dawn. Otherwise, the sky background is too high. Such kind of constraints will not come when we go to space. So I'll give you a few examples also. So first, okay, so before I go to the example, I will show you some simulations. So I hope you can see it. So here I am showing an image of a star with lot of turbulence. So now slowly, if I decrease the turbulence, I can decrease the turbulence by going to mountain tops also, where the disturbance is much low. But once I decrease the turbulence, then I will slowly go and arrive at what I need is my Aries pattern. This is my theoretical limit that I have. So when I go to space, I'm actually removing distortion, atmospheric distortion. So all my starlight will be seen as this Aries pattern that I am showing here. Now, this is the image of the famous Crab Nebula with the ground-based 3.5 meter WIYN telescope. It's a beautiful image of the Crab Nebula. You see filaments, you see a fuzzy, you see nebulosity here. It's an amazing image that you have. But with a smaller space-based telescope, that is the Hubble Space Telescope, you see how it has transformed. You see the finer details that we can see. Size-wise, this is smaller. The Hubble Space Telescope is 2.4 meter and this is 3.5 meter. But there is no atmosphere here to create all the distortions that we have been talking about. So this tells us what is the advantage of going to space. I will show you a few more also in my examples in the coming slides. Okay, now we go to see how from space we can have precision photometry. Now, as you know, this is the era of exoplanet science. 30 years back, we discovered the first planet around a star in a system other than our solar system. So 30 years back, we knew that the only planets that are present in this universe are the planets in our solar system. Now we know that there are more than 6,000 planets which are there in other systems. These are known as extrasolar planets or exoplanets. And they have been detected using various techniques. The first here I have shown, it's a collage of the different techniques through which we have detected and confirmed exoplanets. It is through the velocity bubble, through radial velocity measurements. It is through transits, it is through gravitational microlensing or direct imaging. To give you a little more information, when I say radial velocity measurements, is that these planets are very, very faint and very, very small. We cannot directly image them unless they are in a very nice system where you can actually, they are widely separated. So they have a wide orbit and you mask the host star so that you can see the fainter exoplanets. So this is known as some sort of coronagraphy, and this is through direct imaging you can get the exoplanets. But if you can't directly image them, you have to see the indirect influence that a planetary companion has on the host star. So a planetary companion can give rise to velocity wobble in the host star. And we use, I mean, here we have to use the Kepler's laws to find out the various parameters. So the planetary companion nudges the host star and we see a wobble in the velocity. And from the velocity wobble, we say that there has to be a companion which is giving rise to this velocity variation, radial velocity variation of the host star. Now, if the star is if the star planet system has a good orientation with respect to us, then if the planet is moving around the star and once in a while the planet comes between the star and us, then the starlight will dip like this. And from this, we can say that there is a planetary companion. And of course, there is gravitational microlensing. I will not go into it. Those who are interested can also read through it. And from the right-hand side plot here, which shows the 6,000 plus, this is a slightly older plot. A month back, this number would have changed by now. So it shows the 6,000 plus exoplanets that have been detected till now, and in the plane of the planet mass and the orbital distance, through various techniques here: radial velocity transit, microlensing, direct imaging, astrometry, TTB, etc. And as you can see, a major chunk of it is through transit, this orange points. Now I will explain a little bit more about transits. So if you can see the movie here, so this is the host star, like our sun, and there is a planet which is going around in its orbit around the star. So when it comes, it is going around in the orbit around the star. So here, as it transits, the starlight will dip. As it transits, that starlight will dip. And when it goes back, the starlight also dips a bit, but it is very, very small. So now from this, if you want to imagine, this is sun and Earth-like planet. So you'll have a dip like this. If you have a large planet like Jupiter, the dip will be larger because more light will be blocked. It is very simple to understand that. And what is the dip in the light, or what is the attenuation in the flux that we are observing, or the brightness of the star that we are observing? It is the ratio of the areas of the projected disk of the star and the disk of the planet. And it goes as RP, that is radius of the planet, by radius of the star whole square, because it is pi r square by pi r of the star whole square. So it is RP by r star whole square. So if I have a Sun-Jupiter-like system, this dip will be hardly 1%. And if I have a Sun-Earth system, this is like 0.005%. So this dip, because the planet is so small compared to the star, the dip is very, very small. So we need very precise photometry to be able to see that dip. So I'll show you some results. These are from published results. So this is for a Jupiter-like planet. The left-hand side, it is the same planet, HD 29458b, around the host star HD 29458. The left-hand side is the observation of the same planetary system from ground. And the right-hand side is the observation of the same planetary system with Hubble Space Telescope. Now you can see how precise the photometry is, or how precisely we can estimate the flux of the star. Now, if you see in the left-hand side, this part is very, very noisy. Now, if the dip due to the planet is of this order, then we can never say that there is a planet there. So I'll show you another example. So this is another planetary system, HAT P7, and there is a planet discovered which is confirmed now, HAT P7b. So here you see this is ground based. Look at the noise here. Of course, there is a dip seen here, but look at the observation from the space mission Kepler. I will talk a little bit about Kepler in the next slide. So very, very clean light curve from which you can get. So the kind of precision photometry that we can get from space. Another example, this is a simulation for an Earth-sized planet. I said for a Jupiter size, okay, we see, and we have seen that from the previous two slides. But Earth-sized planet, the dip is expected to be 0.005%. So the dip is this small here, if you can see. And from ground, see, look at the noise. You don't see any dip. So you will look, if you observe this, you will say that there is no planetary system here. It is just noise. This noise is because of the turbulent atmosphere, of the fluctuation in intensity, because of the atmosphere through which the starlight we are observing. Now you go to space. The atmosphere is not there. Whatever noise you are seeing is actually the photon noise from the star itself. And you see how we can very clearly, for the same star, we can see the dip. And from that, we can detect the planet. We can do studies on the planet and get the fundamental parameters of the planet. And this has been a boon that Hubble Space Telescope, sorry, not the Hubble Space Telescope, because of this, this precision photometry required for detecting exoplanets using the transit method. We had the Kepler mission. So it was a boon that Kepler was up in the sky, looking at the same patch of the sky for nights and nights together. Kepler retired in 2018, but it has given us detection of thousands of Earth-sized planets, thousands of planets, as I showed you in that plot of the 6,000 plus exoplanets which have been detected. The major chunk of the transit detection has come from the Kepler mission. And now we have the TESS mission. It is the Transiting Exoplanet Survey Satellite, which is on. And this mission is now, as I speak, is beaming down detections and over detections of exoplanets. So this looked at a same patch because you have to monitor the stars. You have to get rid of false positives. So you have to look at the stars again and again, and then from that you fold the light curve to get this small and small dip, which are your signatures that there is an exoplanet which is there in the system. So now this is about space and precision photometry. Now I come into, in the last 2-3 minutes, I will talk about space and stable imaging. Now you don't have any fluctuation, you don't have blurring of image, you don't have variation, like your atmosphere also varies, right? You have air glow, you have night glow, you have all sorts of disturbances in the atmosphere. When we go to space, all this is zero, nothing is there. We can go to diffraction limited deep field mapping. Now let me show you some example here. Now this is a portion of the sky which is observed with the ground-based Subaru telescope, which is an 8-meter telescope. The diameter is 8 meters. And if you zoom into the central part of the image, this is the blob that you are seeing here. Now the same with Hubble Space Telescope with 2.4, much smaller in size. But because there is no atmosphere, look at the kind of resolution that we are getting. So we go to diffraction limited imaging. And since we can go for longer and longer exposures because all those disturbances, turbulences are not there, we can do very deep imaging also. I'll show you one image here. This is a part of the sky in the Fornax constellation. And if you see here, there is a small square. From the ground, the square looks like a dark patch, not much here. And this dark patch, just for comparison, this is the scale of the moon. It is much, much smaller than what the angular size of the moon that we see on the sky. But with deep imaging with Hubble, this is the kind of image we get, and every dot here is a galaxy. So that small spot that we have a dark patch here, with Hubble deep imaging, it was over 2 weeks, over several orbits of Hubble. This is an n number of images taken. I think it is the exposure time is around 2 million seconds. It revealed the presence of around 5,000, 6,000 galaxies. It revealed the presence of galaxies which are of the age of our universe, that is around 3.2 billion years. It took us back in time. It took us back in time with the deep, stable imaging that was possible from space, and it allowed us to see the universe almost from back to its beginning. So this is the kind of impact that deep imaging from space has. So this justifies that what we lose to atmospheric turbulence, we recover in space as stability and clarity. Removing the atmosphere transforms astronomy from detection limited to precision limited and stable imaging limited astronomy. Thank you. So now I ask Hafiz to let me know if there are any questions.
Yes, the session is open up for questions for now. So okay, so
Yes.
yeah, there is a question.
Yeah, please read it out.
Yeah, sure. How can astronomers distinguish between a young hot star and an old cool star?
Okay. So as I said that the distribution of energy as a function of wavelength of frequency depends upon the nature of the source. So if you have a cool star, say of temperature around say 3000 degree Kelvin, then the black body will peak at a longer wavelength. If you have a hot star, the black body will peak at a shorter wavelength. So if you can observe the star over a wide range in the electromagnetic spectrum, you observe the star in the ultraviolet, in the visible, in the infrared, and look at the spectral energy distribution. From that, you can understand whether it is a cool star, whether it is a hot star, depending upon where the energy distribution peaks.
So the next one is, how does atmosphere turbulence affect visible light observation, and what role does adaptive optics play in improving the resolution of the ground-based telescope?
Okay. So as I mentioned, adaptive optics is to beat the atmosphere. How can we do a real-time compensation of the distorted wavefront that is coming so that we can achieve or go closer to the theoretical diffraction limit of the telescope? So here what we do in adaptive optics, in the optical path of the entire instrument system, you have a deformable mirror. So deformable mirror, it is a small mirror. So what happens is this mirror is deformable, means it has actuators. So you get the distorted wavefront, and when the distorted wavefront falls on the deformable mirror, it then goes to what is known, as I explained, a wavefront sensor. So the wavefront sensor will model what is the distortion in the incoming wavefront and give a real-time input to the deformable mirror to adjust its, to deform the mirror is helped by actuators, and it will deform it so that the outgoing wavefront from the deformable mirror becomes as plain as possible. So it is a real-time input that is given to the deformable mirror by the wavefront sensor, and this is how it compensates. And for visible light, the distortions are much more severe than in the other part of the wavelength band. Yes.
Okay, we have another question. On which characteristics we decide that is an exoplanet?
Okay, so yeah, that's a good question. So you detect a dip now, or in radial velocity measurement, you see a variation in the radial velocity, but it could be a stellar companion also, because you have stars in binary systems. So you have to actually we have to do follow-up observations to find the mass, you find the size. So the mass actually tells you whether it falls in the regime of a stellar companion or a planetary companion. So once you detect the planet, say through transit, you do follow-up observations through radial velocity, because radial velocity measurements can give you information on the mass of the planet. So you have to do that, and looking at the mass, you can say whether it is a planetary companion or not.
So
Yes.
we have time for another question as well, right? So,
we have time for another, just 2 quick questions. Yes.
Sure. So how can a galaxy have the same age as our universe?
Okay, so the galaxy would have formed when the universe formed, the first galaxies, right? So they can have the same age.
So one last question. What are the main challenges in precise photometric measurements in visible light astronomy, and how are they minimized?
Yeah, the challenges, as I have explained, you have to, I mean, if you have to, for detecting, like if you have to be, if you need very precise photometry, say to detect Earth-sized planets around a host star, then you have to go to space, because there it will be only photon noise limited. From ground, it is very, very challenging, because you have to go on taking observations over several transits and then keep folding it so that the noise averages out. But it is extremely challenging, because the kind of dip we are trying to see, or the kind of flux attenuation, is very, very small, 0.005% for an Earth size. For Jupiter size, yes, ground-based can be done, but of course, space-based is always better. And I think I will stop here, because it's time for we just have 2 minutes left for the next one to start. And thank you very much, all of you who were listening. And yes, I agree. Yeah.
Thank you very much, Professor Anandamayi, for a wonderful lecture. And also our thanks to Mr. Hafiz Nasir for well moderating this session. Thank you, both of you.
Thank you.
Thank you.
Thank you.
Thank you.
So I take your leave, sir. Thank you.
Right. Now we are going to the next lecture. This topic is infrared astronomy by Professor Sashikiran Ganesh from Physical Research Laboratory, Ahmedabad. Mr. Goldie Ahuja will be moderating this session. So I would like to briefly introduce the moderator. Mr. Goldie Ahuja is a senior research fellow in the Astronomy and Astrophysics Division of Physical Research Laboratory at Ahmedabad. He is working on comets for his PhD under the guidance of Professor Sashikiran Ganesh, the speaker of today's lecture. With this, I am concluding, and over to Mr. Goldie.
Thank you, Praveen sir, for the kind introduction. So I will not take much time, and I will like to introduce my supervisor, Professor Sashikiran Ganesh. So Sashikiran Ganesh is a professor in the Astronomy and Astrophysics Division of Physical Research Laboratory, Ahmedabad. He completed his bachelor's degree in science at St. Xavier's College, Ahmedabad, and a master's from Department of Physics, School of Sciences, Gujarat University. He joined PRL as a scientist in 1997 after completing a PG diploma in space science and applications from Gujarat University. He has been at PRL since then, and his interests range from solar system bodies to study of the structure of the Milky Way. He has guided 5 students for their PhD in various topics of astronomy. And he has actually over 100 referred publications and over 190 contribution in the astronomical literatures. One of the important results from his work is the discovery of nearly 100,000 stars in our galaxy in the infrared using the Infrared Space Observatory. He is a recipient of the URSI Young Scientist Award and also a 2-time recipient of the prestigious Marie Curie Fellowship. Currently, he is involved in developing a new instrument for near infrared, which actually includes imaging, spectroscopy, and polarimetry called NISP for the PRL 2.5 meter telescope. Thank you, Shishir, and I would like to give you the platform to discuss with us.
Let me share my screen.
Your voice is feeble.
Yeah, I'm coming closer. Is it okay now?
Yeah, fine.
Okay. And you can see my screen. I think, let me just go into slideshow. Is it okay? Slides are visible, right?
Yes.
Okay, thank you so much. Yeah, thanks for this opportunity to talk about infrared astronomy to this audience. So I've just assembled a few space missions which have been flown for infrared astronomy. These are on the title slide here, but we'll go through them one by one and we'll see if, well, anyway, I won't have time to talk about each one of these exciting missions, but we'll see if we can cover a few details. So what are the things I'm going to cover in this talk is listed here. So we'll start with what is infrared astronomy. Initially, what is infrared in the first place? Why is it useful? Why and how do we observe from, whether we can observe from the ground and from space? And I'll talk a little bit about some of the infrared observatories and give you a flavor of results. Because this is a subject which, though young, it has been very active in the last few decades. And it will be, I mean, you could easily have a full session of start programs on this infrared astronomy itself. Anyway, so what is infrared? So before that, we need to understand what is optical light. And the first person to really spend a lot of thought and to document it was Isaac Newton. And although he is more famous for his gravitational laws, but his work in optics was equally important. And he was the one who actually demonstrated that light is made up of different colors. Okay, so, and he was actually the one who also kind of explained how a rainbow is formed and how those colors come up in the night in the sky. So this was sometime in the 16th or 17th century. In the following century, there were further researches on the spectral lines, and then, for example, there were people like Wollaston and Fraunhofer who looked at the solar spectrum and came up with many more features than were visible to Newton, because Newton was using very primitive optics. But by the time Wollaston and others came in, they were able to have much more precise instruments to work with. So this was so these are the lines which people use in modern day astronomy to actually understand the chemical composition of the stars, right? So, but this is all in the optical wavelength. Now, around the same time, there was the famous astronomer William Herschel. And he is more famous for his discovery of the planet Uranus than for his discovery of infrared radiation. But he did some fantastic observations to show that light is made up of much more than just the visible light colors. So how he did that was he had an array of temperature sensors, and these had tips which had kind of balls which were painted black so that they could absorb light coming from the prism. Okay, so the prism had created the rainbow on the sheet of paper in front of him. This is coming from the sunlight. And he had an array of these temperature sensors spaced along the wavelength distribution. Okay, and what he found was that the sensors were showing, they were all higher than the background. He also had a sensor, temperature sensor looking outside the path of the light, and he found that they were all higher than this background temperature, but they were also having a change in the temperature as a function of wavelength. Okay, so the blue and purple were more hotter than when you go towards the red. But the moment, then he found another more interesting thing, that going beyond the red, if he had kept a sensor, he had kept one sensor just to measure the background, you remember. So when he looked at the background, the temperature in the thermometer just beyond the red, he found that it was showing an even higher temperature. Okay, and using various optics that he had with him, he was able to show that the radiation in this region was also following the same laws of optics as the rest of the wavelengths. So that was how he discovered infrared radiation, and infra meaning below. So this was wavelength below red, so that's why it's called infrared. Okay, so that was the discovery of infrared. And then you see, that happened in 1800, but then it was quite some time before people could actually make use of it for anything more than just looking at the sun at this kind of temperatures or at this kind of wavelengths. And that was in 1960s. But before that, I'll just quickly just tell you what is infrared wavelength. I think this kind of plots you must have already seen in many of the previous lectures. Infrared basically is in this region, it's in submicron to micron range. And or if you are more familiar with nanometers, you can say from 800 nanometers onwards. Okay, human eye is sensitive only up to about 800 nanometer here, about 700 nanometer, I would say. And beyond that, you will have infrared and then going to longer wavelengths. Now, why do you need to go to space? That was the question that I think you all would have had to do infrared astronomy, because that's the motive of this series that we are going to talk about, observations from space. So even this plot also you would have seen many times, but what is interesting is these windows. Okay, so this is of course the optical window where we have good transmission, and the entire optical band comes through to the ground with very little exceptions. And then there are, going towards the infrared, going towards the longer wavelengths beyond red, you see that there are a few small pockets where you have again some infrared emission. Okay. And but then, I mean, transmission. So you can see them from the ground, especially if you go to slightly higher altitudes. Okay, we'll talk about that in a moment. But most of the useful infrared radiation is blocked from the Earth's atmosphere. Anything beyond about 20 micron is very difficult to do from the ground. And yeah, anyway, so this we will take it up again later on. So this is again just a zoom of this part, just to show you what exactly is happening in the infrared, going from so this is 1 micron here. So this is all optical window, optical regime here in this range. And then going beyond, we have these small windows where it is perfectly transmitting. Almost 80% light comes through for us. And then as you go to longer wavelengths, you get again smaller windows here. You might think that, okay, in the optical, you're getting only 60% transmittance, but in the IR, you're getting much higher transmittance. So the visibility must be better in, you should be able to see better in the infrared, but it doesn't work out that straightforward. We'll look at it in a moment. Again, you can go, there are a couple of windows in the around 5 micron, but after that, it's completely blocked up to about 8 micron, from where again, you have a few windows. And beyond 14, it is again completely blocked. Okay, most of this blocking is happening because of water vapor, carbon monoxide, carbon dioxide, and oxygen in the Earth's atmosphere. Okay, so if water vapor, for example, reduces with altitude, so then you would expect that that would also improve the transmission from the ground as you go in height. And that is what we are seeing in this slide. This x-axis is the altitude in meters, and the y-axis tells you the atmospheric transmission. We have marked the location of 4 of India's famous observatories which are at different altitudes. Okay, so the sand line here is the Vainubapu Observatory at Kavalur, which is just at 700 meters altitude. And then we have the Mount Abu Infrared Observatory, which is sitting at about 1,700 meters. That is this red line. And then you have the Devastal Optical Telescope, which is India's largest optical telescope. So that is at around 2,450 meters. And then we have the fantastic site of Hanle, where the Indian Institute of Astrophysics is running their 2-meter HCT at 4,500 meter altitude. Okay, so what is interesting to see here is we have plotted the transmission at 3 different wavelengths. Okay, J, H, and K. I should have explained what is JHK. So actually this band here corresponds to the J band. Here you have this window here. Then you have the H band here in this, and then you can define the K band in this 2.2 micron window. Okay. So coming back to this, so as you see a function as a function of latitude height, the transmission improves. Okay, but the best increase, I mean, the best possible compromise is at this location of 1,800 meters, 1,700 meters, where we are located with the PRL's Mount Abu Observatory. So at this height, we have a good compromise of having easy access as well as having good access to some good skies as well. Okay, so that's one big advantage of our location. That is, we'll see if people are interested, we can discuss it in more detail. So when you start talking about infrared, so where you all know Wien's law, of course. So I'm just showing you here what are the different temperatures and where they peak as a function of wavelength, right? So the black body spectrum. So the moment you pick something like 2 micron, you are looking at objects which are going to be somewhere between 500 to 1,000 Kelvin temperature. Okay, so the peak would be somewhere here. And so this tells you that by picking this kind of wavelengths, you are actually looking at signal coming from very cool objects which are cooler than the sun, because the sun is at around 6,000 Kelvin and the peak is in the optical, 0.5 micron. So what is the importance of this, right? So one thing is that you're going to look at cooler objects. And why are cooler objects more important? That's something we'll see in a moment. And then again, when you're looking at this, you can also see that you're going to have different windows which will correspond to different temperatures. Okay, so objects at different temperatures. So suppose you want to look at objects which are around 200 Kelvin or lower, then you should be looking at wavelengths much beyond. Okay, so for example, if it's an object at 200 Kelvin, it will not be radiating anything at all in the optical or in the near infrared. You will need a mid-infrared window in order to observe it. Okay, so we'll show some examples of this kind of observations in a moment. So these are the famous bands I was talking about, which people use for astronomical observations. So beyond the human eye's capacity from 0.65 nanometer, we have the infrared bands, the very near infrared, which is 0.65 to 1 micron. In this we have the R and I bands. Okay, so these are sitting somewhere here in this region. And then we have from between 1.1 to 1.4, we have the J band and H and K. So these are the 3 which are the most common bands which can be used from the ground. Okay, anything beyond that is a bit difficult. Why is it difficult? Because again, we come back to this. I should have mentioned one more point. Now, when you are at 300 Kelvin or you're at 500 Kelvin, you are going to also observe you're going to look at light which is also coming through the Earth's atmosphere. The Earth's atmosphere is also around 300 or 300 Kelvin, right? Or a little lower, but still around that point. So what happens is that as you go to slightly longer wavelengths, the atmosphere and the telescope structure also starts emitting. Okay, so the background goes up, and you have very low contrast between the object and your background sky. So you need to take special techniques, have special techniques to determine the background, subtract that from the source, and then actually the source pops up in the images. Okay, so that's something that we need to do. And that becomes more critical and crucial as you go to longer wavelengths. Okay, so one way that we do for for observing at longer wavelengths is to cool down the entire telescope. Over these bands in the infrared, you need to cool them down to liquid nitrogen temperatures. And as you go down, only the detector needs to be cooled here and the nearest optics. But then as you go to longer bands, you need to cool down the entire telescope structure. Okay. And so that is another big motivation to go into space, because in space, everything will cool down given some time and some proper shielding. Okay. We'll see that in a moment. So as you go to longer and longer bands, you need to go completely to space. Although there are a few sites like in Hawaii and in Chile where we can do some of these M, N, Q, and Z bands, which are possible slightly from the ground. And there are some bands here which can also be done using balloon-borne telescopes, like the ones launched by TIFR from their facility in Hyderabad. This is possible to make use of the balloon to actually observe what happened. Yeah, I hope it's visible. So it's I was talking about the TIFR facility. They are able to observe the C bands, carbon lines at 158 micron using this facility, and that they do by going above the Earth's atmosphere. Okay, to about 30 kilometers altitude, where the water vapor, which is the main culprit in the absorption and the increase in background, that reduces drastically with height. So infrared astronomy at PRL has had a very long heritage. In fact, PRL's Mount Abu Observatory was established for infrared astronomy because we already had several optical astronomy observatories in India. And at that time, the focus was on building a telescope. So this telescope, this 1.2 meter telescope, was built by ISRO's Shar Center. The mirror, excuse me, the optics was made by IAA. And the rest of the instruments that we put up at the focal plane, they were all made by PRL. So here you see one of the very old instruments which were being used. These were instruments which would observe one object at a time. Okay, this was a 2-channel IR photometer. And we would get a signal of how many volts are coming from the source. Okay, so in terms of current. And that would be converted into flux coming from the object by looking at a standard comparison star. This was in the 80s and 90s, and towards the mid and late 1990s, PRL got the first infrared array instrument in India. This was the NICMOS 3 based instrument. It had imaging and spectroscopy built into the system. Okay. And it was the first instrument of its type in the country. In fact, it had a sensor which was on the Hubble Space Telescope around the same time. So that's how the name NICMOS was there. It was used extensively for a long time. And then subsequently, we have the NICS instrument, which is the successor to the NICMOS. And as I told you, we need to cool the detectors down. Okay, so the cooling is done using liquid nitrogen. This is a process where we fill LN2 into this tank here. This is right now. This is when the instrument was being pumped out for vacuum. And then this is mounted sideways here in this position. And then LN2 is pumped in using a pressurized filling system. And the gas gets vented here as the instrument cools down. So this instrument also has imaging and spectroscopy modes. We also implemented polarization modes, but I will not talk about it today. So this was another instrument which has been used extensively on PRL's 1.2 meter. We are now in the process of building a 2.5 meter telescopes instrument for PRL's new 2.5 meter telescope. It will be having imaging, spectroscopy, and polarimetry, all three built into the instrument right from the start. So what do we do with the infrared astronomy? I give you how we observe and why it is important, but what are the objects that we can observe? So we can go with star formation. We can then make studies of the interstellar medium, can understand how galaxies evolve. And as I already told you, infrared means you're looking at the cold universe, okay? It can also be used for probing exoplanetary systems and obviously the high redshift universe. Okay. So significance, let us see in more detail. This is a picture of a Barnard globule, dark globule called Barnard 68. So Barnard was a person who was looking at the night sky, especially the Milky Way. Okay, and this was something like in the late 1880s, early 1900s. And he even used photographic plates, and then he cataloged some of this kind of dark patches with the Milky Way in the background. Okay, and there were people who had been looking at such regions, and they thought they were holes in the heavens, as they called it. Okay, and Barnard was the first person to understand that maybe these are not holes, but actually there's some material in the foreground sitting there, which is absorbing the light coming from the background stars. Okay, so that happened to be correct because later on when we started looking at these regions in the infrared, we started seeing more and more stars. So as a function of wavelength, it is arranged like this. Okay, so you are going in this direction. So these are three images which are basically in the optical. You can make use of normal CCD detectors for them. But the moment you come here, you need the infrared detectors. So 1.25, that's the J band, 1.65, that is H band, and 2.16, that's in K band. So you can see very evidently that compared to the optical, like in the blue filter, you see such a strong absorption. But the moment you go to the infrared, there is decreased absorption. So basically, the extinction has reduced drastically as you go to the infrared range. So this kind of image results in this kind of a color composite, for example, and you can see at a glance how many more objects have turned out over there. And this can be used to study the dark globules. Okay. Later studies have shown that many of these dark globules have a lot of new stars forming inside them. We'll see some in a moment. But many of them tend to be rather cold and inert. So their temperatures must be much lower than 200 Kelvin. Okay, maybe much lower, cooler than that. Okay, so this is another example where, in fact, we have Spitzer Space Observatory data. I will talk about the space observatories in a moment, but I just want to tell you that Spitzer was looking at the night sky in the mid-infrared near about between 3 and 8 micron. Okay, but the Herschel Space Observatory is looking at the same part of the sky over much longer wavelengths. Okay, so you see that there is a strong absorption even in the infrared. Normally, I showed you these pictures which showed that there is strong absorption in optical, but there are some regions where even in the infrared there is strong absorption. Now, if I were to show you an image of this region in the optical, you would see nothing actually, because all of these objects are completely extincted by optical wavelengths. Okay, but the moment you go to longer and longer wavelengths, you start seeing objects in cooler material in emission, And these are all filaments and filamentary structures, which are basically cool molecular clouds, which are feeding into the star-forming regions here. Okay. So these are some of the subjects being studied by colleagues in our institute. Here, I'm just showing you how the extinction looks like using the infrared data. So as we saw here, we can actually estimate by looking at the infrared data, we can actually estimate how much absorption is happening, okay, and how much of material is there. Now, the same technique was used to build this kind of an extinction map crossing 60 degrees along the galactic plane. This was done sometime in the early 2000s using Ganesh, which is a near-infrared ground-based survey at 3 wavelengths, and I used this data for the red clump stars in order to compute this. Okay, this is compared here. This is the same image with a different emission. This one lighting. This part is with the COBE satellite. We'll come to that in a moment. This is again emission by IIRS, and this one is in CO. So there you see similar structures, but then the infrared details show the most significant and much well-defined and resolved structures in the galactic plane. This is an image of the Milky Way galaxy's center, right at the nucleus of the galaxy in the K band. Okay, this was an image we had taken during a visit to South Africa with a small telescope over there. And even in K band, you see some absorption here, but mostly the galactic plane is in this oriented like this. And you get reasonably good view of the center. But the moment you go to slightly longer, this is okay. This is actually the view here is such that you won't see anything in the optical. It's completely absorbed, okay, light from this region. There's almost 40 magnitudes of visual extinction if you would like to understand that way. At the moment you go to longer wavelengths than the K band, so for this you need to go to space. And this was data taken with the Infrared Space Observatory. We had we were part of the ISOGAL survey, and this survey allowed us to look at a large part of the Milky Way's galactic plane. There are selected areas. We could not get time to completely cover the entire galactic plane, but there were regions where there was a lot of interest to cover. So these were images taken at that time. You can see that there's almost 100,000 stars, which were previously unknown, which were discovered just in this much region. Okay, this is just about a few degrees across. Subsequently, this region was again observed by the Spitzer Space Observatory, and this is how the sky looks like if you take the Spitzer wavelengths and the Spitzer resolution, which is much higher spatial resolution. So you can clearly see the galactic center star cluster, the nuclear star cluster, and then you also see a lot of absorption in the foreground dust clouds in the Milky Way. Okay. So this here is a list of the infrared space observatories and space missions which have been launched and which are currently in progress. Obviously, I will not have time to go through each of them, but I'll just mention a few of the important ones. The Infrared Astronomy Satellite. This was the first infrared space telescope launched in 1983. It performed an all-sky survey and discovered huge number of stars which are not visible at all at optical wavelengths. Okay, there were quite a few which we were able to match with optical counterparts, but it could not see any of these. Many of the objects that it discovered could not be studied from the ground. And then later on, there were several observatories which had multiple different purposes, but they also had infrared instruments on them. What is interesting is the Infrared Space Observatory. I already told you about that, some results from that. So it was possible to improve the resolution compared to the IIRS. It had an order of magnitude better spatial resolution, and it had much better spectroscopic capability. And it was able to, of course, cover smaller areas at a time than IIRS, but it went deeper. Okay. Spitzer was even better than ISO. And then after that, we have several other missions. Herschel goes to much longer wavelengths than Spitzer. Spitzer was going up to about 8 micron in imaging, but up to about 60 and 100 something micron in photometry. Herschel went up to 250, 300 micron, and they were more interested in looking at very cold molecular clouds where the temperatures are much lower, and you're only looking at star forming regions or regions where star formation may start up. Okay. JWST is one of the best in the business right now, and it is providing very high resolution images and spectroscopy and photometry. And it's looking at the early universe. We also have another mission from ESA, Euclid, which was launched in 2023 with a very specific question to explain how it was basically a cosmology mission to try to understand why the universe is expanding. So they are looking at dark energy and dark matter kind of material. The future is the plan is for the NGF, Nancy Grace Roman Space Telescope. It's also called WFIRST. And this is going to be launched into L2, which is also the location of the JWST. And it is going to go for, again, wide field infrared surveys. JWST is a pointed observatory, but the WFIRST or Roman Space Telescope will be a wide field survey. So it will be something like IIRS, but going into much deeper range. So IIRS was an all-sky survey, and then later ones are all mostly, okay, even WISE was also an all-sky survey, but all the others are pointed missions. So hopefully we will be gaining a huge amount of information coming from the Roman telescope. So what are the challenges? The challenges for infrared space telescopes are that this entire system needs to be cooled. Okay, the telescope has to be cooled to avoid interference from its own thermal emission. Okay, so what that means is that you have to launch the telescope and the satellite with very bulky cooling material, cooling liquids, usually liquid helium and liquid nitrogen in some cases, but mostly liquid helium. And since it's very sensitive to heat and light, you have to put it in an orbit where it is going to have minimum influence by light coming from the Earth and the Sun. Okay. So basically, L2 is the ideal location where it is going to have fantastic coverage for the rest of the sky. And you need to have detectors which require this kind of cryo operations, and their noise needs to be reduced quite drastically. And so the issue comes down to the point that the technology is such that the cryo coolant required makes it the limiting factor for the age of the mission. So for how long you are able to actually use the telescope. With the JWST, the instruments are going to be cooled passively, and they're going to have big sun shield. They are having sun shields, very big sun shields, and the entire telescope is on the back of the sun shield. So that allows the telescope to be cooled down almost passively. And so that's the kind of ideal location for this kind of work. So here are some views of these telescopes. This one is IIRS, and then we have infrared space observatory. You can see the size of the instrument, the telescope, by looking at the person there. This is Spitzer. This is Akari. It's a Japanese mission. And then you have WISE, and then you have JWST here. So JWST is very unique because it is having a mirror which is almost 6.5 meters across. So it was not launched in this condition, obviously. It was launched folded up, and then it was unfurled in space, both the mirrors as well as the thermal shielding blankets, which you see here. The sun is always on this side, sun, earth are always on this side, and this telescope is pointing here and can be going in any direction. So those are the issues with launching this kind of setups in space. As you can see, all of these, so here they have made use of the solar panels to shield the telescope. So this part is looking at the sun, but this part is looking at space. You have radiation shields, and then you have the entire telescope barrel, which is sitting in a cryostat with liquid nitrogen cooling, liquid helium cooling. Okay. So the same thing with the Spitzer facility. So for JWST, there were several firsts which were seen. I should be stopping soon. So this had passive cooling, and it's cooled it down to 40 Kelvin in space. And there's several firsts which you can see here. And it covers from wavelength range of 1 to 28 microns. Okay, it's got quite a good coverage. These are some of the instruments on board, and what are the things that they are doing. We'll come back to that in a moment. So when you look at the night sky with JWST, so most of the light coming from these objects are in the nearby universe, but all the red objects that you see, these are coming from very distant galaxies, and the light has got redshifted, and that's how they appear bright in the JWST images. With JWST is the first time that we are able to actually see these objects. Okay, this is something for a nearby galaxy, again with JWST, because in the infrared you can see the structures very well, because the most numerous objects in the galaxy are objects which are cooler than the sun. They are stars on the red clump, and these are more easily seen in the infrared. So that helps us to understand the structure of the galaxy. You can see how complex it is. This is a galaxy, so-called grand design spiral galaxy. Just come quickly to the end. This is another view of the same region at near infrared and mid infrared. In the near infrared, you start seeing the stars, but in the mid infrared, you start seeing the cold molecular gas. And some results from that by our colleagues. We'll come back to that if there are any questions. Again, this is an optical region. I mean, this is a region in the infrared, which is dark in the infrared, but the moment you go to longer wavelengths, we are able to see many more structures, okay, in emission. And finally, I will stop with the last slide showing one new structure that we have discovered in the Milky Way using the red clump stars. And we have seen that the outer spiral arm of the galaxy is going beyond, much beyond what was previously known. So this was all done using the TUMAS photometry. TUMAS is an infrared survey, all sky infrared survey. They had two telescopes, one in the northern and one in the southern hemisphere. This was all done from the ground, of course, but then the archival data is available for everyone to work with. And the same is true for any of the infrared missions. All of them are available from a quick Google search. You can download the data and then play with it and understand the universe as it is. So I hope that I've given you a flavor of what infrared astronomy is all about. I think I'll stop here and take questions. And if you're ever at Abu, you will understand why the sky is very good for infrared astronomy here, because usually in winter we have extremely low water vapor and very clear skies. So yeah, thanks. I'll take questions now. Are there any?
Thank you, Professor Sashikiran Ganesh. So I actually can't see questions in the chat itself. Is it somewhere else? So yeah, it's being typed up. Yeah. The questions are not here.
Yeah.
So the first question is, why are telescopes need to be cooled down?
So if I go back to the slide here, I think it's not shared anymore, is it? Can you see
No,
my
sir,
slide?
yes.
You can
You can
see.
still see your slides. Yes.
Okay, just a moment. Yeah, if you look at this this plot, okay, the moment you moment your object is the object is at some temperature, let's say around 300 Kelvin, then it's going to radiate. Okay. So the moment you are looking at objects which are in similar range of radiation as the background that you are looking at, you are going to have trouble. That is why you need to cool down the telescope structures also, apart from the detector, when you want to go to longer bands for observations, because the telescope and the structure supporting the mirrors and the optics, everything, they also start radiating at and emitting at these wavelengths. Okay, because they are warm. So the only way to improve the contrast is to cool down the telescope structures such that they will radiate only at longer bands and not contribute to the signal that you are trying to record. Okay, so that's the reason that we need to cool down the telescopes also. This is particularly the case for wavelengths beyond about 4 micron. Okay.
Yes, sir. Similar on the line, that the question is like, what is cryogenic cooling, and then how does Earth atmosphere affect infrared?
Okay.
And its continuation of this question is also the similar one, which like in ISRO, at which band we can observe from the ground.
Okay. Okay. So the first question was regarding. Okay, I'll take what is the first point. What's the question about
What is
what
cryogenic
bands
cooling?
we can? Yeah. Okay. What is cryogenic cooling? Okay. Cryogenic cooling is when you use liquid nitrogen or liquid helium to cool the uh, object of cool the detector, basically. Okay. So cryogenic is the term that people use. Because this is using liquid nitrogen. Liquid nitrogen boils at 77 Kelvin. That's almost 100, almost 200 degrees below room temperature. Okay. And then liquid helium you need if you're going to fail even lower temperatures like 40 Kelvin or even much lower. Okay, you can possibly go using cryo cooling. Now, Earth's atmosphere affects, as we saw in this graph, Earth's atmosphere affects the transmission of infrared radiation from space to the ground. Okay, so there are some windows where it is the transparency is there, so it is able to infrared light is able to penetrate. About 80% of it is able to come to the ground in this window. For example, this is the H band. Okay, and in the K band you have similar window. And then this width might change depending upon how much water vapor or CO2 is there in the atmosphere. Okay, and then also the height of transmittance. But then you see that there are several windows, several wavelengths which are completely blocked, like this one, and then this part. Okay, and then these small windows here also. So these are completely blocked from the ground. So you have to go to space in order to study these bands. And some of these bands are important because we can observe a lot of molecular emissions in these regions, okay, and 6.5, 7.5. These bands, you have very important molecular emissions from pH molecules, polycyclic aromatic hydrocarbons. So these have signals in this interesting region, and it's important to study them. Okay. From ISRO, from the ground, we have capability of, so from basically from PRL, we have observed up to about 2.25 we have been doing regularly. There have been observations in the L band. Let me show you that. The L band is around 3.6 to 4 micron, okay, in this band. So there have been some observations from India, basically from Mount Abu and also from the 3.6 meter. There are some instruments which are cooled to liquid helium temperatures to get these observations. Yeah, I think that was.
Yes, that answers the questions.
Yeah.
So another question is like, is there a difference between infrared astronomy and the near infrared astronomy?
Okay. So when we say infrared, we generally mean anything beyond what the human eye can see. Okay. So basically, for by that definition, Anything beyond 650 nanometer is considered as near infrared. Okay, and you can go right up to around 200 micron from there. So that's the complete infrared range. Now people have defined different ranges within this range based on what different techniques are required for observations. Okay, so for example, with some detectors, we can go up to about 2.5 micron. In some detectors, we can go up to 5 microns. So near infrared some people extend near infrared to even 5 micron simply because the same detector is capable of observing up to 5 micron. But there are others who will call 3 micron to 15 micron as mid infrared. Okay, so it all depends upon how people would like to use that kind of nomenclature for the different ranges. So for example, here you are seeing that it's 7.5 onwards is mid infrared. And then beyond 20 micron, 25 micron, it's called far infrared. That part is fixed. That okay, far infrared, everybody agrees. Beyond 25 micron, it's far infrared. Yeah.
Yeah, that answers wonderfully. Another very important question is like, how can we study the galaxy with the infrared?
Okay.
So basically that one question is like how to we can actually interpret the galaxies basically using the infrared astronomy, and what more we can actually find out.
Right. Okay. So if you look at this figure, for example, this image. So the most numerous stars in a galaxy are the fainter ones, okay? And they are the cooler stars, and they last much longer, okay? They have much longer lifetimes. And the peak intensities, peak wavelengths are in the infrared, okay? So these are the M dwarf kind of objects, and these are the most numerous in a galaxy, okay? So by looking at it at the infrared window, you are actually seeing the most numerous stars of the galaxy. And because you are seeing in the infrared, you don't have the kind of trouble with absorption as you do in the optical range. Okay, so the same object, if I were to show you the optical image, you would not see this kind of structures at all. So that is why infrared is the best when it comes to observing external galaxies, or even our galaxy for that matter. Yeah, I hope that answers the question there.
Yeah, and similar to this, I think one other question is like, when we view an object through infrared rays, what significant change becomes visible in the object? Basically, compared to visible, what difference we see when we observe from via infrared? I think that answer is similar to that there will be a change because a lot of that extinction will be, the light will be extincted.
Yeah. For example, this place, this Bok globule, which I showed you, let me see where it went. Yeah, this one. So for example, here, you are seeing that in the optical, it is completely absorbed, right? But as you go to longer and longer bands, you have a lot of stars coming up. So that is the important point of infrared astronomy, that you are able to see objects which are otherwise not visible in the optical bands. Because in the optical bands, the light coming from these objects has been absorbed by the dust in front of it. Okay, as you go to longer wavelengths, the dust absorption reduces quite a bit. Okay.
Yes, that answers these questions. Another, I think it's a very curious questions, like why does our telescopes like James Webb need a giant sunshield that looks like a tennis court, while the Hubble telescope doesn't have one? So like the Hubble obviously is launched way before.
Way before JWST. Yeah. So that's a very nice question. So Hubble Space Telescope is in low Earth orbit. Okay, it's almost around 600 kilometer height, whereas JWST is sitting at L2. Okay, which is a couple of million kilometers from Earth. So With HST, the main emphasis was for optical observations, where we do not really require that kind of serious cooling as in the infrared. Okay, so the main purpose was for optical, and they have small heat radiators which are capable of cooling down the structure sufficiently, even though the instrument is not. So basically, they are having radiating thermoelectric cooling on board for that. What that implies is that you need enough continuous power in order to operate those cooling mechanisms. With the JWST, what they have done, because it's a huge telescope, you see, it's 6.5 meter size telescope. So what they have done is they decided they will just make use of the coldness of space. You see, the background temperature in space is around 2 °Kelvin, right? And it's basically the background, cosmic microwave background. So basically, at that temperature, the rest of space would be if you were to allow it to cool down. So what is the source of heat for these is basically the Earth, and then more problematic is the sun. Okay, sun and then Earth's radiation. So these two, if you put them on one side and then block the entire thing using a shield, then that will cool down the telescope, and then it will maintain the telescope at that cold temperature. So it's basically completely passively cooled. And then you have several layers of this radiative shielding in front, so which allows the entire telescope and the detectors to cool down. So when they first launched the telescope, for example, it took them almost 6 months to cool down the instruments before they could actually switch on and see that the instruments were performing as required. Okay, so immediately after launch, and then after it reached L2, so they unfurled the sunshades, and you can see that there are several layers of them. Okay, so each shield will allow an extra layer and level of cooling. So that is the reason that they have kept it like that, and that's one of the constraints that this kind of system has. But then with the passive cooling that they get, they are able to reach 40 Kelvin, and it allows for much longer observations. Otherwise, for the amount of liquid helium they would have to carry for cooling down to that temperature, it would not last long, especially in telescope and detectors of that size.
Yeah, thank you, sir, for answering all the questions. I hope students will get it. I would like to give it back to Praveen, sir.
Okay.
Thank you.
Thanks.
Thank you, everybody.
Yeah, thank you very much, Professor Sashikiran and Ganesh, for an insightful and very knowledgeable discussions followed, and lot of questions still remains. Since because of the paucity of time, we won't be able to attend all the questions. But very interesting lecture, sir. Also, our thanks to Mr. Goldie Ahuja for well moderating the session. Thank you, both of you. And we will be meeting on Monday. So please tune to that, 3 p.m.
Thank you. I'll log off then.
Yeah, thank you.